Hi, welcome to this problem on 2D and 3D trigonometric problems. All right, let's have a look at question 2. We're given a circle with a cyclic quadrilateral ABCD. So the moment I see cyclic quadrilateral, in terms of my circle geometry results, I know a few of them. The most important one being that opposite angles in a cyclic quad are supplementary. They sum to 180 degrees. We're also told that the following property holds true. BC divided by CD is the same as AD divided by AB. So we say they are in the same ratio, they are in proportion. We want to show that the area of this quadrilateral is given by this following formula. Okay, so let's have a look at this quadrilateral and think about how can we work the area of this out. Well, I see the clue here has a DC, a DA, and a sine something here. So what do I know in terms of areas that looks very familiar to that kind of structure? Well, what about the area rule for triangles? We know that the area rule for triangles says that it's half AB times the sine of angle C. Where in a triangle ABC, we know the angle C and we know the side lengths A and B that are adjacent to that angle. So let's try and construct something similar here. So I know they want sine of angle D. So if I construct this line here, CA, okay, we cannot assume that that's a diameter because we don't know if that passes through the center necessarily, but we know it's just a straight line. Now, can you see, I have triangle ADC here and triangle ABC here. So I can say that the area of the quad ABCD is equal to the area of triangle ADC plus the area of triangle ABC. Okay, so if I can just work out the area of these two triangles, then I'm good. Now notice that if this is angle D, then angle B is 180 degrees minus angle D, because if I sum these two together, I must get 180 degrees. That's by cyclic quadrilaterals. So, first of all, for the area of triangle ADC, it's going to be half the two side lengths here, so times AD times DC, which is looking good because there's AD or DA and DC, times sine of angle D, plus a half. So now in this triangle ABC, it's going to be these two lines here. So it's going to be half times BC times AB times the sine of 180 degrees minus angle D. Okay, so now hopefully once we've cleaned this up algebraically and using our trigonometry toolkit, we will hopefully arrive at this result here. Okay, so I'm going to keep this as it is, half times, I'm just going to write it like this, DC times DA times sine of angle D. Okay, that's still exactly the same expression, because multiplication is commutative, and AD and DA is just the same length here. It's this length here. Plus a half. Now, this BC and AB is a bit of an issue at the moment. So let's see if there's any information that was given to us that can help us get rid of that. Well, we were given this following proportion to hold. I can rearrange this proportion if I multiply the denominators across here. So I multiply that by AB and that by CD, I get AB times BC equals AD or DA, same thing, times CD or DC, same thing. Okay, so I can replace this expression here, which is exactly this here, with this expression here. So I can be half times DC times DA times the sine. Now, 180 degrees minus an angle. Okay, so if we look at our cast diagram, so that's going to be in this quadrant here. Okay, so that's going to be 180 degrees minus angle A. And that is in the second quadrant where sine is positive. So by reduction formulae, this is going to be sine of angle D. Okay, so I have half of this exact expression plus a half of that exact expression again. So I have two halves, which makes one whole piece when I add them together. So that's DC times DA times the sine of angle D. And that's exactly what we wanted to prove. All right. Okay. And then lastly, we want to show that this result holds true. 2 times CA all squared plus CD all squared or equals CD all squared plus DA all squared plus AB all squared plus BC all squared. Okay, so CD is this length here, DA is this length here, AB is this length here, and BC is this length here. Okay, so it's saying that if we square all those sides and add them together, then we end up with CA, which is this line here, squared and then multiplied by 2. So let's think how we can solve this. We just previously shown the areas of these two triangles using the area rule, okay, for two triangles and then adding it. But what rule do we know that deals with squares and triangles? Well, Pythagoras comes to mind, but there's no 90 degrees here. So what other rule do I know in trigonometry? What about the cosine rule? The cosine rule says in a triangle that if you have triangle ABC, okay, and you want to work out that angle, or sorry, if you know that angle A, and you know the side length here B and C, and you want to work out this missing length A here, then the cosine rule says A squared equals these two sides squared and then added, minus 2 times the product of those two sides, times cos of the angle included between those two sides. Okay, so I think let's give that a try and work out CA, this base here of those two triangles, in two different ways, and then probably add them if we want to get two amounts of them. Let's see. Okay, so it's triangle ABC. So in triangle ADC, we have the following. Okay, so if we want the length CA, so CA squared equals this length squared, so CD squared, plus this length squared, so DA squared, minus 2 times the product, so 2 times CD times DA times cos of angle D. Okay, now in triangle ABC, we can work out CA squared as well. It's going to be this side squared, so BC squared, plus this side squared, AB squared, minus 2 times the product of those two sides, AB and BC, times cos of the angle included. That's 180 degrees minus angle D. Okay, but let's see if we can clean that up. So it's going to be BC squared plus AB squared minus 2 times. Now, if I use the same proportion here, okay, so I get, if I cross multiply again, I get AB times BC equals AD times CD. So I've got AB and BC, so I can replace that with this expression here. And why do I want to do that? Because I see I've also got it here, and hopefully I can get those terms to cancel, because we don't want any causes in this expression. So it's going to be 2 times CD times DA times cos of 180 degrees minus angle D. So again, if we draw a cos diagram, 180 degrees minus D is in this quadrant here. Okay, let me just go back up here. Yeah, I was meant to say angle D here, not A. Okay, so cos is negative in the second quadrant. Okay, because only sine is positive in the second quadrant. And because we're reducing off a horizontal from 180 degrees, cos remains the same, but it becomes negative cos of that angle D. Okay, so cleaning up that further, that's BC squared plus AB squared. The minus minus becomes plus 2 times this expression. Okay, so putting all this information together in both these triangles, if I add the left-hand sides, I get 2 amounts of CA squared. That means I must add these right-hand sides. So what do I have? I have my CD squared, which is good, that's what I wanted, plus my DA squared, that's what I wanted. Okay, now there's going to be a minus 2 CD DA cos D here, and a plus 2cd dA cos dI. So those terms will cancel when you add them together. And then what's left over are these two terms here, AB squared plus BC squared. And that's exactly what we wanted to show here. All right, so this problem relied on not just knowing our important trigonometric formulae such as the area rule and the cosine rule, but also that we needed to use the proportion given to us here appropriately and to use some circle geometry results, namely the cyclic quadrilaterals, opposite angles being supplementary. All right, so this is a perfect example in terms of a mathematical question that has many facets of the different areas coming together and using them to problem solve. All right, I'll see you in the next one.